Hi, everyone. I'm Chris. I'm so happy to be here. I've always wanted to go and speak at a Laracon, and here I am, and it's very surprising, and I'm very grateful to be here. By show of hands, who's enjoying themselves at the conference so far? Yeah, everyone. You can put 2 hands up if you like as well. I'm very happy to be here, and it's an honor to be here, so thank you very much to Sean and the rest of the organizers for making that happen. Now, the talk that I'm going to do today is based on the work of a very influential and clever Ruby developer and functional programming advocate called Tom Stewart. And because we're in that area of the woods, I want to ask you to take a look at this book, Understanding Computation. It's a fantastic book describing computation from the earliest models of Turing machines up to what's used today. There's a lot of clever code and learning along the way, and you'd be very well off to read it. You can get it from Amazon, or I guess O'Reilly, or bookstores. So take a read at this, it's quite good. But today we are here because I want to impart one thing that I want you to remember, apart from the awesome exercise that you've done, which is appreciated. I want you to know that monads are just an ordinary data type. It's a difficult topic for people to talk about or to listen to because functional programming in general comes from a very mathematical background, and the way that these things are explained are usually with heavy maths or bad analogies. And we're not going to do any of those things today. Today we're going to look at other data types and to get your mind into the rhythm of the content of monads, and we're going to look at how monads work without technical jargon. And you will learn that you're already using them. You maybe just don't know what they're called or how to reuse the ideas of monads to better suit your code. So I'll start with a question. And Frank, the very skilled mic thrower down here, is going to throw the mic to someone who feels willing to try and answer the question, what is a stack? Please, someone try. Oh, up there, Frank. That's maybe a bit far. Is anyone down at the bottom willing to try? There's a hand up there, Frank. What is a stack?
It's a data type.
Yes, it is.
And first come, last served. Or first come, last out.
Yes. Yes. So that's the description I was looking for. Thank you very much. Can you throw the mic back? I don't know, Frank, you've got to up your game there. OK, a stack is a data type. And data types tend to have operations and rules, things you can do with them and behavior that they adhere to. The operations and the rules that I'm interested in for a stack are as follows. In terms of operations, I want to be able to make a stack and to push a value onto it. I want to be able to get the last value I put on the stack off. I want to be able to see what the top value in that stack is. And I want to be able to tell if it's empty or not. There are some rules that go along with this. For instance, if I push a value on and I look at the top value, it's got to match the value I just pushed on. That makes sense, right? If I push a value on and pop it off, I need to have what the stack was originally before I pushed the value on and popped it off. If I push a value on, it shouldn't be empty. And if I make a new one, it should. These aren't too complex rules for it to follow. But given the operations and the rules, I forgot to start my timer. Given the operations and the rules, we can start to create implementations that are vastly different internally, but they look the same from the outside. We could, for example, implement them however we like, beginning with an ArrayStack. This is perhaps not the most elegant implementation that you'll see of this, but it works. It has the methods that we expect, the operations, for pushing and popping, for looking at the top value, and for seeing if it's empty. It does that by accepting an array of values in the constructor, and then acting in a pseudo-immutable kind of way allows us to push values on and pop values off using the built-in PHP array functions. Top just fetches the previous one if there's anything on the stack. And empty just checks whether there are anything, whether there are any values in that values property. So we can create a new stack, and we can push individual values on. And if we run this code, we'll see, let's look at what we should see. The top value should be, shout out, 2. Is it empty? No. And what do we get if we pop?
2.
No, we don't. We get the stack with just 1 on it. But it's good going. So 2 for the latest thing we pushed onto it, false because it's not empty, and the stack before we pushed 2 on just had a 1 on it. OK, that's an array stack. What about a different implementation, like a linked list stack? Does the same thing. Construction looks a little bit different, but it behaves in the same way. So for a linked list stack, we can have a head element, and then a list of items in the tail, assigning them to properties. When we push a new value on, we take that value and put that at the head, take all the other values and put them in the tail. So we're going to get a kind of nesting going on. When we pop a value off, we get rid of what's in the head and just return the tail. When we want to know what's at the top, we return the head. And if the tail is null, then we know it's empty, because we only potentially have a value in the head. And we shouldn't have anything in the tail. So we create a new instance of linked list. We push a value on. We push another value on. What's the top value? It's 2. It's not empty. And if we pop it off, we should see. We should just see 1 in its value. Internally, it's going to represent that slightly differently, but essentially, it's the same thing. 2 is the value on top. It's not empty. And the only value we have inside of it is a 1. That's pretty interesting. We can define more operations in terms of the behavior we can expect from the stack. We can, for instance, define a size method, in this case as a trait, using the methods we know already exist there and requiring them for anything that uses this trait, which, by the way, you can do if you have a trait and you want to depend on functionality in the class that's used in the trait. You can declare those methods as abstract, and then the class that uses it needs to implement those. So we require isEmpty and pop behaviors to be defined, and we use them in here. If it's empty, return 0. Otherwise, pop a value off, get the next size through a recursive call, and add 1 to it. It's kind of like unwrapping it and adding 1 to a counter as we go down until it's empty. It's an interesting way of implementing a size method. But what it does is it gives us a way to define behavior that we can share across implementations without knowing how those implementations are made. We don't need to know if it's a linked list stack with a head and a tail. We don't need to know if it's an array stack with some kind of internal array. We just need to know that it implements isEmpty and pop. And we can make this shared behavior. So stack, apart from being an abstract data type, is a kind of specification. Because we've defined operations and rules. And we've seen that as a specification, we can implement it a bunch of different ways, as long as we adhere to those operations and rules. And the result is that we have an interoperable data structure. It's a common interface for us, those 4 methods. And we can use them to implement shared functionality. OK, what's a collection? We need the mic thrown again. Please. What's a collection? Who feels like volunteering this? It's a lot simpler than everything I've just spoken about. What's a collection? I'm just going to wait, actually. Good chance for some water. You need the mic. Oh, fine. Sit down. Oh, there's great. Awesome.
Nice throw. It's a set of data.
It's a set of?
Data with functions to get data out of it or put data in it.
Sort of. It's not exactly the answer I was looking for, but I applaud the fact that you volunteered. At a much simpler level, can you chuck the mic back, please? Oh, this is so fun. Okay, at a simpler level, it is, okay, so it is something that you can put data in, but for the purposes of this talk, I'm going to define a collection as something that you can, that has operations and rules, and the only operation I want to define is that you can call in each function on it with a callable, and it'll run that callable for every item in it. Does that kind of make sense? Well, it does to me. This is the only operation I want to concern myself with in the case of this collection. Given a collection of some values, I want to be able to give a function to that and have that function run on each of the values. So the rule we can define as each calls a function 0 or more times, because it could be an empty collection, in sequence with the value each time. Given those operations and rules, we can implement them however we like. We could make an array collection, taking in a list of arguments using this spread or rest syntax, and assign that to a property. And then our each function can step over each value and run the callable against them. So we can create a new array collection with 1 and 2 and 3 and 4 and 5. And we can run the each function on them. And when we execute this code, we should see 1 and 2 and 3. That's a simple implementation of collection in the simple way that I've defined collection. We could create a different implementation, a range collection. This works more like the range function, where we have a start and an end, and the kind of steps we want to do in between them. And so our each function could create some kind of pointer that steps through each value until it gets to the end of the range. And it runs the function for each of those. It's kind of an esoteric implementation. But when we define it like this, what we expect to see is 1 and 2 and 3 as the result. Similar to what we got with the array collection. And so again, we can define more operations given more shared functionality given the operations and the rules that we defined for our collection. We could create a filter method, knowing only that our implementations implement an each method. We can use that to create our own kind of filtered list. If by executing that function the value is not falsy, we can add it to the list of filtered items and use it as a trait, similarly to what we did with our stack implementations and that shared functionality. And so we can define an array collection, we can define a range collection, and we can filter them. And we've been able to make this filter function without knowing how they're implemented internally. We can just use the trait. This isn't going to run because I've removed all that extra code in between. So anyway, collection for us now is a kind of specification as well. There's a common interface of just that one each method. And using that common method, we can create shared functionality, like adding a filter method, or a reduce method, or a map method. And those implementations would be similar to our filter method. So what are stack and collection? I'm not going to wait for the mic to be thrown around this time. Stack and collection are abstract data types. We began with this idea, and I called a monad an abstract data type. But stack and collection, as we've seen, are kinds of abstract data types. They define an expected behavior, and however they're implemented, as long as they adhere to that behavior, it doesn't matter to us, because we can use the behavior that we know is there and create new functionality. So let's do a refactor. Now that that is out the way. Have a look at this code, which is not uncommon in some code bases I've seen before. We have an address class and a store class. And addresses can be created and assigned as properties of store objects. So if we wanted to, for instance, get the name of the city for a store, a naive method might be to take the store, use property access to get address, use property access to get city. And using this information over here as a bit of setup instructions, what should we see if we run this? You can just shout it out, it's fine. Amsterdam, yes. Let's run it just to make sure. Amsterdam. Okay. Now, what's the problem with this code? What's the problem? Yes, if no one assigns an address, it's going to throw an exception. We can see that by commenting this out and running it. It says null, but it should be exceptional. I think I'm squashing exceptions for this REPL. And that makes sense, because we're trying to get the city on the property address, which has null, and what do we do in that case? It is an exceptional case. So although this is pretty neat code in terms of understanding what it's trying to do, it's pretty brittle code, because if someone uses it in a way that we don't intend and aren't securing against, it's going to break. For this purpose, we could create an object called maybe. This has sometimes been called optional. There's a particular set of functionality that I'm interested in us trying, though. To begin with, we need to have some way of constructing it. And this code in the middle here just ensures that if it is an instance of maybe that I'm trying to make a new instance of maybe, that it unwraps it and then rewraps it. It's not really essential code. But anyway, we have a constructor that accepts a value and assigns it to a property. We have just a shortcut to be able to use fluent syntax to create new instances. We have a way to get the internal value out again, because that's important as well. If we've got to use, if we send a string in and we want a string out at the other end, we've got to have a way to unbox it again. But the bit that's interesting for me is this bit here. Maybe, or optional, creates a way for us to implicitly null check, which is what this code should be trying to do. And so we can change our getCityForStore method to start using this, where we wrap store as a maybe, and then we try to get the address and wrap the result of that as a maybe. We try to get the city and wrap the result of that as a maybe. And so at the end, what we should have is a not. We shouldn't have an exception in the case where we haven't assigned an address. So it still functionally works the same. It just might not throw exceptions so much. This isn't the kind of code we want to write, though, is it? I mean, by show of hands, who would be happy changing the previous code to this? Because this is a mess. I don't expect you to put your hands up. This is a mess, right? There's too much boilerplate here to solve what should be a simple problem. So let's try and refactor this a little bit to make it easier to work with. Let's say that instead of using try and property access, let's rather use a callable that will give us a value if it's not null and allow us to execute something on it. Maybe we change this to being callable. And let's do something like, if this is a value, then return whatever that function is, given the value. That seems okay. So now we could do something like, if we have a store, then return store address. And if we have an address, return city. Let's see if this executes. I think it will. Null. Who can spot what I've done wrong here? Ah, that's right. Yes, very good. Well spotted. OK. So it's a little bit more flexible now, because we're not dealing just with property names, but it's more code now. So what are we doing? I think a bit of the problem is that we are creating maybes the whole time. So maybe, we could instead do something like static create from inside here. Being careful now that we're not returning a scalar value, potentially, to also create an empty maybe as a return value, in the case that something is null. And in that case, I guess we could start to do something like this. And so maybe we just return that and right at the end call value on it. That seems a little bit better. Let's see. Does that work? Yes, it does. Just to make sure that we're not going to get some exceptional case, although I think I'm squashing exceptions, commenting it out in this case wouldn't render an exception. Oh, it does. What have I done? Wow, what have I done? Hold on. Where's the error? Maybe construct too few arguments. OK. So I think here I would just call that with null. And it's useful that it's getting to that point, because have a look here. I disabled this address, which means this check is going to be a null kind of value, and it's getting to this point. So that's good. That error was actually helpful, despite how it's just shot my blood pressure up. But now it seems that this is maybe not exactly doing service to what the method is trying to do. I'd prefer to use a more universal term for this method name, something like then. And if that seems like a bizarre choice, you'll see why later. I've picked that. OK, this should still work fine. There are a couple more optimizations I'd like to make once I restore this relationship. OK, so it's working again as we expect. For starters, I think since property access is so universal, I would like to fudge things a little bit and define a magic getter. And in this case, what it would return is something like this then using name. Wow, I'm so nervous. OK, function value using name if value name. So we're going to do our null checking in here as well. Do we need to do it in here? Oh, anyway. Return value name. So something like this, where we could potentially revert back to using property access. Address. Oh, thank you. Well spotted. No. No, because look, that's a good question. Doesn't it need to return a maybe? And the thing is that this is still running through this then, which means it's going to wrap as a maybe here. We potentially don't even need this here. We could potentially even just do that. And I'm hoping this still executes. Yes. So we didn't need the extra null checking. But it's a good question. The thing is that because we use this then, it already does the wrapping for us. OK, so this is looking a little bit simpler. Now, the fact that we have to box the variable and unbox it is symptomatic of a system that doesn't understand the concept of maybes yet. We've made an isolated function that can deal with maybes. But if our wider system learned to talk in terms of maybe, like say, for instance, Say, for instance, we accepted maybes and output them as part of our system design, then we could go back to our original code. Store address city. And the only thing that would change is how our system feeds that information in. Maybe, and at the end we want to print the value. No. New maybe. OK. So if our wider system is capable of talking in maybes or optionals, then How we initialize that data might be a bit more complex, and how we unwrap it at the end might be a little bit more complex, but we can start to work directly with optional values. And our code can be that same stupid, naive code that we had before, only now it's not, because it's doing implicit null checking for us. And we can at any time disable the relationships, and we should be better off than we were before. This may seem a little over the top in terms of refactoring, but it's a concept that I'm going to use to illustrate the relationship between different kinds of monad-like things. It's a really easy starting point for us to continue from. What about how we deal with many things? What if we have a blog that has any number of categories, and those categories have any number of posts, and those posts have any number of comments, and we want to build, heaven forbid, a tag cloud? How would we do that? Using some kind of shortcut flat map implementation, which is incredibly gnarly code, and utilizing at the same time short array closures, short arrow closures, which I'm happy to talk to you about afterwards, just as a kind of shortcut for function. We can create a kind of flat map implementation. And then we can define a function like getWordsForCategories, which accepts an array of categories and goes over each category. So for each category, get the posts, and for each post, get the comments, and for each comment, get the comments full text and split it by spaces. And if we define some posts and some categories, and we run all those things through this function, we should get comments which represent the kind of intellectual maturity of internet comments in general. Yes, that's an interesting observation, how this money's first. This does what we want, right? It's horrible code, though. It's horrible code. I mean, forget how flat map is implemented. This code here, I don't know, it's sort of, I don't know, I feel it's horrible anyway. So how do we make this better? We could try to create a new thing called many. And though this looks pretty similar to our maybe or our optional class in terms of how it constructs and how it allows fluent syntax and how it unboxes values, when we have a then method on this, what we wanted to do is take all the internal values, step over each, and apply a mapper function to them. Okay. So let's use that, or let's start to use that in here. And as we go along, we're going to do some refactoring for this as well. What I expect us to be able to do, I'm going to comment this out, is to be able to say something like return many create categories. To be able to call then on that with a function for each category. And I'll use arrow functions for this as well. So for each category, you return the category posts. And then for each post, return the comments. And then, I'll just paste that there. For each comment, return the words split up again. Do you think this will work? I hope it'll work. Will not. I'll take that bet. Let's run it and see. No! It doesn't. Why not? Oh, very good. Does this work now? I lost the bet. Well done. The output's the same, right? The code, arguably, is a lot better. This sideways pyramid that we had before has become not so indented, and it's a little bit easier to see maybe what we're attempting to do. But like we did with maybe, we can also add a few shortcuts to this as well. Something like public function get, doing the same thing here, but anyway, get return this then. I'll use a short arrow function for this. And we'll return value name. Yes, thanks. $. Okay. Now, I'll copy this because I want you to see the improvement to structure that we're doing. But now we should be able to say posts, comments, ooh, that's interesting. And again, if our system is built to understand the concept of many, and we change our expectation here from array to many, with that same kind of output value, then we can do away with this, and we can do away with this. We still have to have the then because we're not returning the array directly. We're doing something with the value in it. But now we can define this as many create, returning a value. And hopefully this still works. Yes, there we go. Because if our wider system understands the concept of maybes and manys, this starts to become the code that we can write and format. Which is not an entirely uninteresting prospect. I think you'll agree with me. But why are we doing this? Why refactor this code at all? We've seen some commonality between maybe and many. And the fact is that maybe and many are actually very similar things. The only difference, in fact, if I delete this create, is in how their then method is implemented. For maybe it's a case of, well, if the value exists, then run it with a function. For many, it's a case of, if the value exists, run each of those values through the function. Maybe and many are monads. They, in essence, because of their operations and rules, are an abstract data type. Just to look at what those operations and rules are again, for a monad, typically, it has the operations of being able to create an instance of itself with some input values, and then do something with those values. But not just do something with those values. When you call then on a monad, it should run that function 0 or more times, and always returns an instance of the same type as itself. With maybe we saw, if there was a value, we run the function with it, and we wrap the return of that as a new maybe, or null, if that value doesn't exist. And for many, we saw when we called the function, we run the function against each of the values and wrap the result of that in a new instance of many. And the behavior there is that we can run function 0 or more times, and it always returns an instance of itself. And in terms of creating a monad, as long as it doesn't alter that internal value, it's fine as well. We should be able to create a new instance of a monad with a value, like string foo, and immediately call a function to unwrap it again, like the value function, and that value should be the same. And so monad is a kind of specification, just like stack and collection were. It's a common interface, thens and creates and value function. And because of that common interface, we can build shared functionality. We can connect multiple operations from different monads together. To give you a kind of example of this, though it's not too in-depth an example, we're going to look at some code. And it's going to demonstrate to us this concept over and over, that maybe doing the next thing will happen if the value is not null. That for many, doing the next thing will happen for each value. And using this behavior, we can define something like a within method. Just something to run a function against each internal value. Given a function, we can call a method we expect, like then. We can execute it and wrap its value in another method we expect, called create. And if we use that within maybe and many, then when we've created a maybe, calling within, using this kind of functionality, it will take the internal value and it'll run string to upper on it. We can define this exact function. I'm going to do this quickly. Something like, hold on. I want to show you how much we can reuse this functionality. If we say something like up is the short closure, and we call maybe with up and get its value. Let's see. These do slightly different things, though. I think I'll revert to my previous code, just show you that. Of course, I can't run this now because I've taken all of maybe and many's bodies out. But the idea is that we can define functions that run within the within method. And because we're using that same trait in different kinds of monads, and depending on the shared functionality, it's not going to break in unexpected ways. So when we add the within method to the maybe monad, and we define a function to run on the value, if it's maybe there, the result would be something that we expect. Similarly, if we create a list of items as a maybe, and we run a function using the within method, we're going to get results that look like this, where each item is run according to that function. Okay. So where are you already using this? Because you are, by the way. Since you're at a Laravel conference and since you've done any amount of web development, you're already using this. Hands up if you've heard of the promises spec in JavaScript land. Yeah, quite a few. There's implementations of promises in PHP as well, like React PHP and AMPHP. If you've used jQuery, I guess, or if you've used the fetch API in JavaScript, you may be familiar with this concept of executing a function and then calling a then method on it, giving that another function, and that function being executed eventually when the network request terminates. If you've used jQuery, you've used a monad-like thing. jQuery, in case you're unfamiliar, a lot of us were tortured with this back in the day before beautiful things like Vue.js and React.js came along. But jQuery looks similar to this, or you'd see a lot of this kind of code in your jQuery projects, where you use a CSS selector with this special $ function, and any amount of elements can be returned from that, including an empty list with no elements in. But you can continue to chain things on that, like filter or adding events via the on method. And so most of the methods in jQuery would give you another jQuery-like object when you run them. And in that sense, it's very monadic in structure. Another example of this is with Eloquent, particularly fluent syntax. So we can write queries in Laravel applications that chain little operations on top of each other. And internally, there is a query state that gets built and built and built and built. And at the end, when we execute the query, all of that gets resolved down to a neat little SQL query. But we can continue to chain operations on this. We can do wheres and betweens and select specific columns. And it's quite a powerful tool built around this concept of repeated functionality. And at the end of the day, monads are good for repeated operations. In terms of maybe, the repeated operation is implicit null checking. In terms of many, it's a repeated flat map or a repeated iteration over some internal values. For promises, it's to call a function eventually when the value resolves. And for promises specifically, we see this often because we will do something like requesting a URL and then calling a then on top of that to execute when the URL resolves. Doing something inside that then, and then calling another then, and then calling another then. It becomes quite a chain of things. But the repeated behavior there is to call functions when values eventually resolve. For jQuery, the repeated behavior is filtering and modifying elements in the DOM. For Fluent, it's repeatedly changing a query. And every subsequent method call returns an instance of the same monadic thing underneath. So, when you see yourself repeating operations, maybe consider how you could be using a monad-like thing. Because you can make more of these kinds of structures. You don't just have to be a consumer of this. And now that you understand the connection between how these objects work, the thinking about how you can create new types of this abstract data type, maybe you could make monads as well. And try using them. Don't shy away from using fetch or from using fluent. Try and use them and see how they can be useful for you. See how you can reuse this concept to make your applications better and more maintainable. And tell your friends about them. This is probably the biggest thing. Don't wait for your friends to have to go to a conference and hear someone else confuse them about monads. Because I presume you understand roughly how they work now in terms of being just normal data types. It's not something secretive or special or beyond your ability to explain. Point them at Fluent, and point them at promises, and point them at optional types. And then try and identify to them what those things have in common. I think that's all I've got. Are there questions?
Hi. So in these examples you showed us, there were quite a bit of magic things going on, with both of them having the magic getter. Mm-hmm. Is this a typical way of implementing the monads? And if that's so, wouldn't it be complicated for the junior developers?
It's not a typical way of implementing them. It's just syntactic sugar on top. No official definition of monads includes that magic. It's just something I've felt can be useful to shorten a lot of calls to then with a callback.
Okay, thanks.
So this was quite a easy and fun introduction. What if you were going to go from the other direction and present something magic, crazy, and really, really confusing to show how clever you were? What would that be?
In this topic?
In this topic, what's the crazy, crazy, amazing thing you can do that would confuse the hell out of all of us?
I wouldn't be able to. I think I have seen a very good example of magic for this that is not something that I would have thought of. But when we got to the section about defining shared behavior across monads, and I did a within method, given the structure of both maybe and many that have this then method, it is and has been demonstrated to me feasible to create shared methods and chain their execution through monads. So you could create, I didn't show an example of this because I had a slide later on about it, but using promises, you can demonstrate the refactoring from callbacks on requests to using promise with then. Using that along with the within shared functionality, you could start to chain an eventual or a promise monad to resolve into a many monad, like commits in a Git repo or comments in a blog post, and then run a method through within with that. So you start to chain different kinds of monads just based on their shared functionality, like the then method, where you create a promise, and when that resolves, you use that to create a many, and then for each many item, you use that to create a maybe, and you stitch it together like that. I think that's a practical and magical thing to do, but I didn't feel confident pulling it off in the talk. There's a question at the back there. Oh, okay.
So I guess the definition of a monad was the operations and rules and specification, but I still have no understanding of what the word monad itself means. Where does it come from?
I don't know. It's a lot of the functional programming concepts I find are very mathematically based, and so sometimes the terms are borrowed from that. I don't know what the actual word means, but if you understand the bits that it does? I don't know. That's a good question. Does anyone here know where the word comes from? Yes? It's a Greek word. Monada, which means the entity of one. Thank you very much.
Sort of helps.
Okay, well, if you have more and you want to ask them, you can shout out at me on Twitter, and the slides are up at that URL if you want to go over this again. I think particularly the refactoring slides are useful to go over and just try and walk through the process of how we get from naive implementation to verbose, more safe implementation down to a concise thing that does a whole bunch of implicit magic. But yeah, thank you.